We're now going to look at the Thevenin and Norton theorems. We'll spend most of our time on the Thevenin theorem, but then show that the Norton theorem is just a derivative of the Thevenin theorem using source transformation. Now, you should be familiar with, at this point, and have watched the previous videos covering linearity, superposition, and source transformation. I'm going to leverage off of those in deriving or proving Thevenin theorem and then using it in an example. So Thevenin theorem says that any one-port network comprised of linear elements, this could be resistors and dependent sources at this point, later that would include capacitors and inductors, along with independent sources, will have the same terminal characteristics, in other words, load line. We talked about load line in the source transformation video, so watch that if you don't know what is meant by load line. Will have the same terminal characteristics as an equivalent circuit, which we'll call the Thevenin equivalent circuit, comprised of just two elements, a single independent voltage source in series with a single resistor, or in general it would be some linear impedance, which would be a combination of resistor, capacitor, and inductors. Now, a one-port network is just simply well, this right here is a one-port network. So a port is a pair of terminals. We typically talk about two ports or one port, so a two-port would have a pair of terminals on one side, pair of terminals on the other. A one-port simply has one pair of terminals. So that's what we're looking to replace. If you draw a box around part of a circuit, and there are just two terminals that enter into that box, you can replace all of what's inside that box with an equivalent Thevenin circuit, which has just a voltage source and, in our current context, a resistor. And this is very beneficial and, well, simplifying when we're interested in studying the interaction of that one port with whatever it's connecting to. Okay, so let's prove it first. I'm going to do a loose proof, but the goal is for you to see where this comes from. So we're going to leverage off of superposition. Okay, remember that if we have, I'm going to kind of, rather than draw a circuit, I'm going to go back to this idea of a system that has inputs and outputs. So if we looked at in the superposition, we had an example, I think, where we had a voltage source, an independent voltage source, and an independent current source. And those were, we treated those as like the inputs or the excitation to the system. So here's some linear system, it's a circuit, and we're interested in some response, maybe a voltage, could be a current, we'll just call it Vx right now. And what we found with superposition was that for linear systems, the response, any response in the system, any current or voltage, is going to be a weighted sum of each input. Okay, so I'm going to just use some Greek letters here to be fancy. We'd say that Vx, some response, is going to be a weighted sum of the two input sources, Vs1 and Is2. Now, in general, we want to extend this idea by thinking of some bigger circuit here. This is a linear network, and we'll have multiple. Maybe I drew that too big. We'll have multiple sources here. And so I have current voltage sources, and we'll have current sources, as such, and we could call them V1, V2, Vn, I1, I2, In. Okay. So lots of independent sources driving the system, and we look at some response. So we're going to look at say the output, we'll call it a voltage Vx. And maybe this is, some voltage that's across some internal resistor. It doesn't matter what it is, it's two nodes. It's the voltage across between two nodes in this linear network. And sorry, that's Vx. And we would say, in general, that Vx is going to be a weighted sum of all of the voltage sources, which I've numbered V1 through V capital N. And so we'll say alpha sub little n times V little n. Okay, that's just the weighted sum of all of these sources, like alpha 1 V1 plus alpha 2 V2 plus dot 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 alpha n V capital N. That's what this is. Plus all of a weighted sum of all of the current sources. Oops. Again, beta 1 I1 plus beta 2 I2 plus dot 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 beta m IM. Okay? So all we're doing there is just extending the idea of superposition. Now, we're going to consider a slight modification here. We're going to add something to this circuit. If we add, suppose, a current source out here, okay, I'll give it a value Ix. The question is, how does that Ix modify our response? Okay, Vx. I'm going to copy all this down here. Oops. Alright, and we're going to modify this. So I could have just as well put this current source somewhere inside here, right? Which I wouldn't draw it in here. I would move it out. I'd put it out here, and I'd say, okay, we'll just connect it in like I drew the other ones, right? But we've chosen to stick it across the terminal pair where we've defined Vx. So there's nothing fundamentally different about that. But now, so now we're wondering, how does it change the voltage Vx? Well, it's just another current source. Okay, all of the current sources previously were just contributing some weighted contribution from that source to the output. Now the first question is, do either of these terms change by adding Ix? According to superposition, we found that if the system is linear, we can use superposition, which says we can determine the contribution of each independent source to the response of the system by turning off all of the sources except for that one, computing the response, and then adding that to each response due to every other source acting alone. So if we turn Ix off, which is what we had originally before we ever added Ix, we found that the response from all these sources at Vx was just exactly this term right here. So that's not going to change when we add Ix. The only thing that's going to change is that we're going to now have a new term. Actually, this in a different color. And our new term will be something times Ix. Now the response we're looking at is this voltage Vx, right? And so we can say that whatever we're going to scale this Ix current by will have to have units of what? It'll have to have ohms, right? So I'm going to actually use the symbol R. I'll call it Rx. Okay. Now all of the rest of these terms here, what units do they have? Well, they contribute to the output Vx, so they're a voltage. So I'm going to call them V, I'll put sigma for the sum of everything else, okay? So let's rewrite this. We're going to say, therefore, Vx is equal to V sum plus Rx times Ix. And here we're just focusing on how does Vx get impacted by adding this current source across the one port. Now, we've seen this before. We can draw a circuit for this, an equivalent circuit, right? Now, although in this case it's representing our particular, this one port with all these sources, it has the equation of, has this equation here where Ix is on the horizontal axis, Vx, actually I did that wrong. Let me plot it this way. It starts at Vz, or V sigma, and let me plot minus Ix, and we'll see why in a moment. And if we do that, we have a slope of minus Rx. We've seen that before, that's a load line. Well, we could get the same load line by using a single voltage source and a resistor. The resistance would be Vx, the voltage source would be V sum, and the current, the voltage across it is Vx, and the current leaving here is minus Ix, because remember Ix was defined as going in, right? You see this right here, it's going, this is Ix. So what we have just shown is that we could get the same, we could achieve the same terminal characteristics at Vx if we replaced all of that linear network with those n voltage sources and m current sources with a single voltage source V sigma and a single resistor Rx. All right, and this is the Thevenin theorem. We just proved it. So this is equivalent to this voltage source, which now we will call V Thevenin, but it's just V, it's our V theta, or V sigma, and we'll call it R Thevenin, which is just this Rx. Okay, let's put that to use in a problem. So find the Thevenin equivalent circuit. So let me draw something here. Okay, so we have R1, R2, V1, I2. So most of the work in using the Thevenin or Norton theorems is actually the technique of how one solves for finding the Thevenin resistance or Thevenin voltage. And what I'm going to draw upon here is what we talked about in the superposition, no, in the source transformation lesson where I talked about load line. So just a quick review here. If we have this load line where we have a voltage and a current I, call this V, I'll call this V open circuit here for now. You'll see why. So V and I, what we found is that you have a straight line. It has a y-intercept of V open circuit or V Thevenin, these are equivalent, and it has a short circuit current, I short circuit SC, a slope of minus R Thevenin, and the short circuit current is equal to V open circuit divided by R Thevenin, and the open circuit voltage is equal to R Thevenin, you can show R Thevenin times I short circuit. And I mentioned this before, that you have these three terms, the Thevenin resistance, the open circuit voltage or the Thevenin voltage, and the short circuit current. And you only need to find two of them in order to uniquely specify this. So when solving for a Thevenin equivalent or problem, you ultimately want to be able to draw the Thevenin equivalent circuit, which requires a Thevenin voltage, or Thevenin open circuit voltage, and a Thevenin resistance. But the way that you come about those can be either through finding them directly, or you could find the Thevenin resistance and the short circuit current, or you could find the open circuit voltage and the short circuit current, right? You can find any two of those, whatever two are easiest to find, and then use those to get to your open circuit voltage or Thevenin voltage and Thevenin resistance. Okay, so I'm going to work this problem now. This is a simple problem because it has no dependent sources, and I'll show you a dependent source example. Simple problem, no dependent sources. And the technique is very easy to find the Thevenin resistance and open circuit voltage or short circuit current. First is to find R Thevenin. All you have to do to find R Thevenin is turn off all independent sources and find equivalent resistance between, we'll call this A and B, so these are terminals between A and B. Now think about it. If you have if we have this network up here, this Thevenin equivalent network, if you turn off the independent voltage source, V open circuit or V Thevenin, that V Thevenin source is due to all of it's the net acting of all of the independent sources in the original network. And so if you turn that off, you see that all you're left with is R Thevenin. So when you look in, you see just R Thevenin. Well, you do the same thing to the original network. Turn all the independent sources off. So let's do that. We're going to have a short for V1. We're going to have an open for I1 or I2, right? And now we look in between A and B, and what do we see? R Thevenin is simply going to be equal to the sum of R1 and R2. Now, secondly, we need to find either open circuit voltage or short circuit current. Either one of them will do. And we look at the circuit and we say, which one can we find most readily? So think about that for a moment. Make up your mind. Okay, I see simplicity in finding the open circuit voltage. If I look for the open circuit voltage, then I have no I, right? This I here is going to be 0, which means if there's no I flowing through R2, there's no voltage drop across R2. Let me go ahead and draw this for clarity here. So we will have V1, R1, I2, and then R2, there's no current. Since there's no current, this V open circuit here will simply be the voltage across this I2. This is going to be V open circuit. And that's easy to find because by KVL around this left loop, I can easily see that V open circuit is going to be equal to V1 plus whatever is dropped right here across R1, and it'll be R1 times I2. And so now we can draw our equivalent, Thevenin equivalent. We'll have a resistance, R Thevenin, that's going to be equal to R1 plus R2, and we're going to have an open circuit, a Thevenin voltage, that is going to be equal to V1 plus R1 plus I2. So if we had originally 2 volts, 2 ohms, 1 amp, and 3 ohms. Then what we would have equivalently now would be 5 ohms, the sum of the two, and V Thevenin would be 2 plus 1 times 2. Oops, that's a multiplication there. 2 plus 2 ohms plus 1 amp, that's going to be 2 or 4 volts. So we have a 4 volt source and a 5 ohm resistor, and that is equivalent to our original network. We now want to look at a slightly modified example, and you'll notice that what is different in this example is that we have a dependent source. Now, how do you think we'll go about finding our Thevenin? Well, before we said turn off the sources. Turn off the sources, and so we might think, okay, well, we'll turn off all the sources, which means we short the voltage sources. So here's a short for the V1. We'll have our R2, and now we say, what do we do? What do we do with this dependent source? It's a voltage source. Can I short it? If you short it, then the R Thevenin would be equal to just R1. So before answering that, let's consider a little more closely what this dependent voltage source does. Notice that it puts out a voltage that is 2 times the current I1. I1 is right over here. It's actually the same current that is flowing through it. So let's think about this. If I have a dependent voltage source that is defined as follows: I, and then we have 2 times I. Okay, the voltage across it now is going to be equal to, according to this voltage source, it says it's 2 times the current flowing through it. So this 2 has to have units of what? 2 ohms, right? Because I'm getting a voltage from a current. Now, could I put something else inside this box which would have the same terminal characteristics, VI characteristics, as that dependent source does? Well, I need to put something in there that produces a voltage V that is equal to 2 times the current flowing through it. Any ideas? It's too simple, right? It's a resistor, a 2 ohm resistor. So we see that a dependent source, if it depends on if it's a current source, a voltage source that depends on the current flowing through itself, or you can show that if it's a current source dependent on the voltage across it, that's nothing more than a resistor. It's just a sneaky way to describe a resistor. So now that we know that this dependent source in this configuration, meaning it is dependent on the current flowing through itself, is actually a resistor in disguise, is it possible, and we've solved the problem, this example problem, when there was a resistor, R1, right? Is it possible that the Thevenin equivalent resistance is actually just R1? And we have to say, because of what we just discovered here, no. All right, and we have a problem now. If there is a dependent source or more in a one-port network for which we are trying to find a Thevenin equivalent, we cannot just turn off the independent sources or the dependent sources. We have to leave them in there. So let's leave it in there. I'll draw it this way. In this particular case, we actually could go ahead and replace this with a resistor, but I'm not going to do that because I want to demonstrate in general how we go about testing or determining the Thevenin resistance for a network, a one port that does have a dependent source in it. Okay. So we're going to leave the source in there, and now we have to figure out how are we going to find what this Thevenin resistance is. Well, what is characteristic of a dependent sources is that they don't show their character until they're stimulated. Okay, you don't know exactly what voltage or current they're going to produce until the dependent variable actually has a non-zero value. So we have to externally apply some energy, some current or some voltage to this this network now. So that's what we're going to do. We actually apply a test current or a test voltage. Now in this case, we're going to apply a test current, and the reason we're going to do a current is because this dependent source actually depends on the current flowing through it, and if I connect a test current, and we'll use a 1 amp current source to the one port, then that current's going to flow through I1, or will be I1. So how are we going to get R Thevenin? We'll say that R Thevenin, right, this whole thing is equivalent to some R Thevenin. Remember, we have our independent sources turned off. So if I apply 1 amp to my R Thevenin, then the voltage I should measure here would be equal to 1 amp times R Thevenin. In other words, R Thevenin can be found by simply taking the voltage that we measure when we apply 1 amp and divide it by 1 amp. Okay? So what will be the voltage in this case? V will be equal to 1 amp times R1 plus 2 times I1, which I1 is just the 1 amp. So we see that V is equal to R1 plus 2 times 1 amp. And therefore, R Thevenin, which is equal to the voltage divided by 1 amp, is R1 plus 2, which is what we know before having done this. We know that's what it had to be because we discovered that in this case this dependent source was actually equivalent to a 2 ohm resistor. So therefore, R Thevenin is equal to R1 plus 2, and we find our V open circuit again as we found before. So I'm still going to use the open circuit as opposed to short circuit, and if we do the open circuit, it's easy to find this because when we have just, let's see, when we have V1, we have our dependent source, and we have I2, that's all that's happening because there's no current flowing through R2. And this voltage is really just then 2 times I1, which is I2 in this case because it's the same current. So V open circuit is going to be equal to, V open circuit is V1 plus 2 times I2, and that is what we found previously. So in the end, we have an equivalent network that has a Thevenin resistance and a Thevenin voltage source, just as we would when there was no dependent sources. It's just the method in which we find each of those that may be modified when there's a dependent source, or will be modified when there's a dependent source. In closing, we want to introduce Norton Theorem, and this is conceptually identical to Thevenin. So Norton's theorem, I won't write it out, but it says basically that a one-port linear network, or a one-port network comprised of linear elements and independent voltage and current sources, can be replaced with an equivalent network which is comprised of an independent current source and a parallel resistance. And we'll call this IN and RN. So this is a Norton equivalent. And this is equal to, or we can make it equivalent to, should never say it's equal, but at the terminals it would be equivalent to a Thevenin equivalent that would be made up of Vthev and Rthev. And this is equivalent to our original one port. All right, one port with linear resistors. Well, let me just say with linear elements and independent sources. Okay, so we could just as well find the Norton equivalent as we find the Thevenin equivalent. The nice thing is that through source transformation, these can be readily related. So for instance, if you're asked for the Norton equivalent, but you actually go about finding the Thevenin equivalent, it's easy to go from one to the other. Let's relate these. Okay, we did this in the superposition, in the source transformation video. And so we would write here that V Thevenin is equal to, that's the open circuit voltage, right? So open circuit voltage is equal to V Thevenin for the one on the right. So let me start this over. The open circuit voltage for the Norton equivalent is going to be just Rn times In, right? If there's no current flowing out here. And the open circuit voltage on the right here is just V Thevenin. The short circuit current on the left for the Norton is going to be just In, because when you short across here, all of the current, you got a current division, but you've got infinite conductivity, so all the current will go through that short rather than Rn. And that is equal to V Thevenin over R Thevenin. So therefore you can relate these. So let's use that as an example, or go back to our example, and find the Norton equivalent for this first example that we worked. So here we had the Thevenin equivalent for that example. All right, and now if we were asked and said find the Norton equivalent, all we would do would be, recall in source transformation the resistance does not change, so Rn is equal to R theta, and so that's going to be equal to 5 ohms. And In, the Norton current, will just be equal to the short circuit current of the Thevenin circuit, and that's going to be 4 volts over 5 ohms, 4/5 of an amp. So if you know how to do Thevenin equivalents, you can do Norton equivalents. When you go to solve problems, you'll find that, again, I think I mentioned before, that you just need to find 2 of the following 3: open circuit voltage, short circuit current, and R Thevenin. So whichever 2 are easiest to find those, and then you can compute the third one to arrive at either a Thevenin equivalent or a Norton equivalent, whichever one you're being asked to provide.